Have you ever made ice cream at home? An ice cream machine? The old-fashioned ones are a churn, right? And there's this bucket, and then there's a smaller bucket inside that has this paddle in it, and you have to crank it, or maybe you have an electric one. Well, you put ice in the outside bucket, but if you just use plain ice, the ice cream will never freeze. You have to put salt in it. Why do we need salt? Salt is going to lower the temperature at which that saltwater solution freezes to about negative 10 degrees Celsius. And we will see this when we make ice cream in lab next week. We'll be putting ice in a big Ziploc bag, and it'll begin to melt, and we'll take the temperature of it, and it'll be about 0 degrees Celsius, because once the ice starts melting, it stays at 0 until it all melts. And then we'll dump some salt in there and just squish it around a little bit. And you can just watch the thermometer drop. And it'll go down to close to minus 10. It doesn't happen when you put salt on your food, does it? Right? You put salt on ice, and the temperature drops. This is crazy. This is called a colligative property, and there are several colligative properties. What these have in common is that they depend on the number of particles that are dissolved in the solution. It doesn't matter what those particles are. It could be sugar, it could be sodium and chloride, it could be potassium and acetate, or anything. It's the number of particles. Colligative properties of electrolytes are going to be a little different, and we'll talk about those at the end, because electrolytes separate into ions, right? So 1 mole of an electrolyte is going to form more than 1 mole of particles. 1 mole of sodium chloride is going to form 1 mole of sodium ions and 1 mole of chloride ions. That's a total of 2 moles of particles, right? Instead of something like sugar, a mole of sugar will dissolve in water and you'll have 1 mole of particles. Vapor pressure lowering is a colligative property. The vapor pressure of a solution that has a non-electrolyte solvent is lower than the vapor pressure of the pure solvent. So we talked about vapor pressure, and here we have a beaker with a watch glass on top, so it's a mostly closed system. And we have this dynamic equilibrium. We have water evaporating into the gas state, and we have water from the gas state condensing, getting stuck back into the liquid. If we add a solute to this, the solute is going to get in the way. It's going to block some of the surface of the water. That's the simplest way to think about it. And so it's going to lower the rate of evaporation, because the particles have to get to the surface, the water molecules have to get to the surface in order to evaporate. Well, if there's other things at the surface, then there's not as much surface area available to them, right? And we said that the rate of evaporation depends on surface area. So that's going to slow down the rate of vaporization. The rate of condensation will not be affected by that. And so initially we're going to have faster condensation, but then as less and less gas is present, then that will slow down and will eventually establish a new equilibrium. But in this new equilibrium, there are fewer molecules in the gas phase.
Does the temperature also be affected or no?
The temperature will not be affected, no. That's a good question. Any other questions? So the solute particles getting in the way is a simpler explanation, but a more fundamental explanation is nature's tendency towards mixing. So this is kind of crazy. So we know that if a pure solvent and a concentrated solution are in the same container, they're naturally going to mix, right? And they're going to form a less concentrated solution than the original. We talked about the aquarium with the salt water and the fresh water. And you take the barrier out and it's going to mix, right? This will also happen in a sealed container with two separate beakers. So this looks like a cake plate, right? If you've got something like this at home, you can try this at home. It's going to take a while, but one beaker, you could use a drinking glass. One beaker has pure water in it. The other beaker is a concentrated solution. Dissolve a whole bunch of salt or sugar in some water. And then you wait. And as time goes on, the water level in the pure water beaker will go down, and the water level in the concentrated solution beaker will go up. And those water molecules are literally traveling through the air into this beaker. So how is this working? So we have evaporation here, and we have condensation. We have evaporation here, but the evaporation is less. And then we also have condensation. So from this beaker, the rate of evaporation is greater than this beaker. And so water, the net result is that water is evaporating from this beaker and ending up in the concentrated solution beaker. Kind of crazy.
So in a solution, you put like a sugar solution, there are more sugar molecules at the top of the solution.
Well, in a sugar solution, the sugar molecules are going to be evenly distributed within the solution, but they will necessarily be taking up some of the spots on the surface, right? In pure water, all the surface molecules are water molecules. But when you have a solution, now some of those are solute molecules. And so that reduces the rate of evaporation of the solvent. Any other questions? Of course, anything cool, we have to have an equation and make math and ruin it, right? So this can be quantified, and this is called Raoult's law. The partial pressure of a solution is equal to the mole fraction of the solvent. And so you asked earlier, would we ever be interested in the mass percent of the solvent? Well, not the mass percent usually, but we would be interested in the mole fraction of the solvent times the partial pressure or the vapor pressure of the pure solvent. So this is the vapor pressure of the pure solvent, the mole fraction of the solvent, and this is the partial pressure of the solution. So vapor pressure is directly proportional to the amount of solvent in the solution. If we have pure water, what's the mole fraction of water? 1, right? And then 1 times the vapor pressure of water gives us the vapor pressure of water. If we have something else in there, then the mole fraction for the water is less than 1. And we multiply by the vapor pressure, and so the pressure of the solution is going to be less than the vapor pressure of the solvent. So the vapor pressure of a solution is lower than the pure solvent, and we can, rearrange some things here and come up with an equation that gives us the vapor pressure lowering the change in the pressure. And so the change in the pressure is the mole fraction of solute times the vapor pressure of the solvent. These two equations can kind of get a little confusing. They'll be given to you if needed on the exam, and you just need to pay attention to the subscripts here labeling mole fraction of what, pressure of what. So calculate the vapor pressure at 25 degrees C of a solution containing 55.3 grams of ethylene glycol and 285.2 grams of water. Excuse me. The vapor pressure of pure water at 25 degrees Celsius is 23.8 torr. So 55.3 grams of ethylene glycol, 285.2 grams of water, vapor pressure of pure water, 23.8. The 25 here and the 25 there are not going to come into the calculation. But you have to use the vapor pressure for the temperature of the solution, right? It has to be at the same temperature. Okay, so let's identify what these things are. So here, this is the vapor pressure of pure water. So we can call that P0H2O. That's the vapor pressure of pure water, 23.8 torr. We're trying to calculate the vapor pressure of the solution, not the vapor pressure lowering, just the vapor pressure. So then we want to use this equation right here. So we need the mole fraction of the solvent, and we were given the partial pressure or the vapor pressure of the pure solvent. So the equation we're going to use is P solution equals mole fraction. Yeah, the screen probably is shaking.
Oh, I thought it was me shaking.
Well, actually, it's not the screen, it's the projector, because the train's going by.
Oh.
And those things hang off the ceiling, and you probably can't see from there, but there's some styrofoam trying to wedge the projector up against the ceiling tile to reduce some of the shaking. But yeah, it happens. And yeah, if we have an earthquake in this building, we probably wouldn't notice, right? Because it's always shaking. One of these days it'll fall down, but we'll be gone by then. So the mole fraction of water times the vapor pressure of pure water. So we've got this. We need the mole fraction of water. The mole fraction of water is going to be what? It's going to be moles of water divided by the total number of moles, which is the moles of water plus the moles of ethylene glycol. And I'm going to call him EG because his name and his formula are too long. So we have some little side calculations to do here. In video games, these are side quests and they sound fun. Not so much here. We need to convert these masses to moles. So that's our ethylene glycol, and we're going to use the molar mass. We're going to have grams on the bottom and moles on the top. And 2, 4, there's 6 hydrogens times 1.008, and there's 2 carbons times 12.01, and there's 2 oxygens times 32, 94.07. So 55.3 divided by 94.07 is 0.58787 moles. And then for the water, I guess I'll do that over here. 285.2 grams of water. Divided by the molar mass of water. So 285. 285.2 divided by 18.02 equals 15.827 moles of water. So now we can plug those values in here. We want moles of water on the top. and we want the sum on the bottom, whoops, 15.827 plus 0.58787, and the moles cancel out. I'm getting 0.964. That's the mole fraction of water. Well, it makes sense that this is a large number, closer to 1, because we've got a lot of water and just a little bit of ethylene glycol. So in terms of moles, the mole percent would be 96% water, right? The pressure of this solution is going to be 96% of the vapor pressure of water. This is what you do to a percent if you want to multiply, right? You divide it by 100. So here we've got our mole fraction times the the vapor pressure of pure water. And so this is going to have a vapor pressure of 22.948, or 22.9 torr. Any questions? Did anybody do that calculation with me? Did I do something wrong? It was coming out a little differenter than I expected. Does anybody care? I don't think anybody cares. The moles is different?
Ethylene, I had 0.5, 0.056.
Let me just double check it. 53 divided by... Yeah, I don't know what happened. I don't know. Okay, so we were talking about non-volatile solutes. Remember, volatile means it evaporates easily. If the solute is volatile, then it's also going to contribute to the vapor pressure of the solution. We talked about ideal gases. There's also such a thing as an ideal solution. Ideal solutions obey Raoult's law at all concentrations. And so in that case, the total pressure above an ideal solution is just the sum of the partial pressures of the solute and the solvent. You just add them together. But of course, we also have non-ideal solutions, and these do not always follow Raoult's law. And this is because of interactions between the solute and the solvent molecules. If they like each other a lot, that's going to reduce how much they evaporate. It's going to reduce their vapor pressure. If they don't like each other very much, then it can increase the vapor pressure. So what the heck are we looking at here? This is vapor pressure going from low to high as a function of the mole fraction of component A. So starting out with 0A, it's all B. Up here, this is the vapor pressure of B, And as we increase the amount of A and reduce the amount of B, these lines come down. We end up here at the vapor pressure of pure A when the mole fraction of A is 1 and the mole fraction of B is 0. So the vapor pressure of the solution is just adding the point on the blue line and the point on the red line, and we get this purple line. So that's what an ideal solution does. If we have strong solute-solvent interactions, they are going to not want to evaporate as much. And so the vapor pressure for A is going to be lower. It's below that dotted line. That's what we expect. It's going to be lower because it kind of likes those other molecules and it doesn't really want to leave just yet. And for the other component, it's also going to be lower. And so then when we add these together, we see this dip here. At the ends, it's still the same because here we have pure B, and here we have pure A. There's no interactions. This is the opposite situation where the solute-solvent interactions are weak. They're like, I'd kind of like to get away from you. And so the vapor pressures are going to be higher, and so then we're going to see this bulge in the middle. So vapor pressure lowering is going to happen at all temperatures. Here we have a phase diagram. Right? We've got solid, liquid, and gas. We're looking at temperature increasing this way, pressure increasing this way. So here at 1 atmosphere, we can travel across and we'll come to the melting point of the solvent. This blue is the pure solvent. And if we keep going, we're going to get to the boiling point of the pure solvent. Well, the vapor pressure is going to be lower for the solution. So the red is for the solution. Here we can see the vapor pressure is lower. And it's a little harder to see over here. So what happens is, as we're going across, we get to the freezing point of the solution before we get to the freezing point of the solvent. And we keep going along, and we're going to get to the freezing point of the solvent boiling point, and then the solution's going to boil at a higher temperature. So this is going to be boiling point elevation, and this is freezing point depression. And here we have a picture of someone putting antifreeze into the radiator of their car. Antifreeze is an aqueous solution of ethylene glycol, and it works a lot better than water because the ethylene glycol is a solute in the water, and it causes the freezing point of the water to be lower. So that's good if you don't like your radiator to freeze solid, which is really bad because it expands and then it like bursts the radiator, and then you need to go get a new one. And it's also good at the other end because it causes the water to boil at a higher temperature, and so you're not going to have all that steam coming out of your radiator as easily. And it's kind of ironic that I just had my daughter's car towed this morning because there is some hole in it somewhere, and if you pour water or anything into the radiator, it just comes out onto the road. So.
Did she hit something under her car?
No, it's a 95 Oldsmobile.
Oh.
You know, these things happen like every other week. So because of the vapor pressure lowering, we have a lower melting point and a higher boiling point. So freezing point depression can be quantified using this equation. Delta TF, that is the change in the freezing point, that is equal to the molality of the solution times a factor. This is like one of the very few places that we use molality in general chemistry. But we're using it here because we are talking about solutions at different temperatures, right? The molality doesn't change, the molarity does. Molality is a measure of how many moles of solute are in a certain amount of this solvent, right? So it's the number of particles. Delta TF is the change in the freezing point. And it's normally reported as a positive number. I don't like this, but they didn't ask me. Normally delta means final minus initial, and that's not the case here. So it's always reported as a positive number, and then we have to think about it. Am I supposed to add that or subtract that to find the new freezing point? Here we have normal freezing points and freezing point depression constants for various solvents, also normal boiling points and boiling point elevation constants for those solvents. You might need to refer to that table to do some of the homework problems. So calculate the freezing point of a 2.6 molal aqueous sucrose solution. So 2.6 molal is the concentration, and we want the freezing point. Well, we just learned that the change in the freezing point is equal to the molality times the freezing point depression constant. So we need to know what that is. Here is water, 1.86 degrees Celsius per molal. KF 1.86 degrees Celsius per molal. And they gave us the molality, 2.6 molal. So we're just going to put these numbers in here. I've got 2.6 molal times 1.86 degrees Celsius per molal. The molalities cancel out. 2.6 times 1.86, 4.836 degrees Celsius with 2 sig figs. Common mistake is to report this as the answer. This is not the freezing point. This is how much the freezing point changed. It's freezing point depression. It can be helpful to draw yourself a little thermometer. So here's our thermometer, right? And the liquid comes up the middle. And then, here we have 100 degrees, that's the boiling point. And here we have the freezing point of water at 0. So I remember as a student being confused about which one goes up and which one goes down, right? They move away from each other. The boiling point goes up and the freezing point goes down. Or another way, if you don't like cold weather, we're getting, it's November and the weather's getting chilly, and some people find that depressing. So freezing point, depression, okay? So that goes down, and then they get excited when it gets hot in the summer. That doesn't work for me because I'm kind of the opposite, but it might work for you. So this is the normal boiling point of water. And so what's going on here is that the the melting point is going down. This difference is 4.8. So then the freezing point is negative 4.8 degrees Celsius. Okay?
So if the terminology was saying calculate the boiling point, you would add 4.8
Yeah.
in this situation?
Yeah, in this situation, you'd have to use the boiling point constant instead.
Oh.
But yeah, you'll get a positive number either way.
Oh.
And you have to add to find the boiling point and subtract to find the freezing point. Yeah. The math is not hard, but it can be confusing. Pardon me? You would add to 100. Mm-hmm. Yeah. And we'll do one of those in just a minute as well. The math is not hard, but the subtracting part can get a little confusing. So, draw yourself a thermometer. Minus 4.8. So boiling point elevation, the equation is almost identical, but here it's the change in the boiling point. It's the molality of the solution times the boiling point elevation constant. So the antifreeze prevents the radiator from freezing, and it also prevents the water from boiling. Okay, let's calculate the boiling point of a 3.6 molal aqueous sucrose solution. So aqueous solution here tells us that the solvent is water. We're going to need that boiling point elevation constant for water. It's 0.512. We also need to know what the normal boiling point is. We should know that for water, but I don't expect you to know that for anything else because I don't know, right? So our normal boiling point's 100, and the constant is 0.512. Okay, we're looking for boiling point, and we've got this molality. So the molality is 3.6. That's another train, isn't it?
It's getting a little obsessive.
Tracking the trains. I don't know why. I find it very amusing. KB 0.512 degrees Celsius per molal. So change in the boiling point is the molality times KB, 3.60 molal times 0.512 degrees Celsius per molal. Okay, so boiling point elevation, freezing point depression, vapor pressure lowering. Another colligative property is osmotic pressure. So osmosis is the flow of solvent from a solution with a lower solute concentration to one of a higher solute concentration. And this is the process by which drinking seawater causes dehydration, right? Because when you're drinking salt water, it's more concentrated than the fluid in your cells, and osmosis will make the water go from the low concentration to the high concentration, and so it'll actually draw water out of your body. And this is another one of those things. You have to remember the direction it goes. So I think of it this way. Nature is like trying to make everything the same, right? And so it's wanting to mix stuff up. If you can't have the solute moving, then the solvent is moving. And the solvent's saying, well, it's not very concentrated here, and it's really concentrated over there, so we better go over there to bring that concentration down. So that's what the solvent does. So this involves a semi-permeable membrane, and that allows some things to go through, but not others. So biological cells have lots of various kinds of semi-permeable membranes. And so the ones we were talking about in your gut are going to allow water to pass through, but not going to allow the sodium and chloride ions to pass through. So here we have an osmosis cell. This we used to call these U-tubes, but that's something else now, isn't it? We have a U-shaped tube, and there's a semi-permeable membrane here that will allow water particles to go through, but not the solute particles. And so we're going to start with a concentrated solution on this side and pure water on that side. And at the beginning, the levels of liquid on each side are even. So what's going to happen here is water molecules are actually going to be going both ways, right? They're going to be going from the pure solvent into the concentrated solution, and some of them are also going to go from the concentrated solution into the pure water. But the ones going from the solution to the pure water have solute particles in the way. So it's just like with the evaporation, the solute particles are getting in the way. So they can't go through as fast. And so the rate of movement from pure solvent to concentrated solution is greater. And so over time, what we'll see is the water on this side will move to the other side. The level in this arm will be higher, and the level in this arm will be lower. And this looks like a manometer, right? We did this with mercury, and the difference in the heights represented the difference in pressure. So the difference in heights here, now this is water, and so it's measured in like millimeters of water or something instead of mercury. So it's a very small pressure, but this pressure is known as the osmotic pressure. This is the amount of pressure that you would have to apply to this side to prevent osmosis from happening. Have you heard of reverse osmosis? It's a water purification system, the reverse osmosis. Well, how does that work? Well, it's the opposite of this, hence the name reverse, right? So you've got your tap water that's got stuff in it, and the system applies pressure here to cause osmosis to go in the reverse direction, forcing the water to come out this side. And so the particles and contaminants that you don't want are stuck here, and then you get your pure water over there. But you have to use energy to do that. You have to apply pressure. So osmotic pressure, the pressure required to stop the osmotic flow. This is the equation for osmotic pressure. That's a capital Pi. It's the molarity of the solution times the ideal gas constant times the temperature in kelvins. So this is our old friend from, what was that, chapter 6. So let's calculate the osmotic pressure in atmospheres of a solution containing 1.50 grams of ethylene glycol in 50 milliliters of solution at 25 degrees Celsius. Now this is not as easy as the boiling point and freezing point ones because they're not saying here is the concentration that you need. They're going to make us calculate that. But we have a mass of ethylene glycol, and we have a volume of solution, and we have a temperature. And we are trying to find the osmotic pressure in atmospheres. So osmotic pressure is equal to the molarity times the ideal gas constant times the temperature. R here is 0.08206 liter atmospheres per mole Kelvin. Our temperature is 25 degrees Celsius. We need to convert that to Kelvin. So that's 298 Kelvin. And we need to calculate the molarity, right? So the molarity is the moles of ethylene glycol per liter of solution. So we've got 1.50 grams of ethylene glycol. And of course, I don't remember what that molar mass was, so we'll just calculate it again real quick. Yep, 94.07 grams per mole. So 1.50 divided by 94.07 gives us 0.15946 moles. 0.0155946 moles. And we need the volume in liters. We have it in milliliters. We can pull that trick. Milli means times 10 to the minus 3. So 0.31891 liters. Sorry, moles per liter. So now we've got the numbers we need. 0.31891 moles per liter times 0.08206 liter atmospheres per mole Kelvin times 298 Kelvin. Look, the moles cancel, and the liters cancel, and the Kelvins cancel. So 7.80 atmospheres is the osmotic pressure of that solution. Did I do it right? No?
I think the molar mass is right.
62.068. At the main molecular molar mass.
It's around, I think it's around 62.
2 times 12.01. You're saying this is 62?
62.068.
The 2 times 12 and 6 times 1 and 2 times. We're just failing all over the place tonight.
Yeah, I think it's 62 because the molar mass. But at the main molecular.
How am I getting this wrong? 2 times 12.01 plus 6 times 1.008 plus 2 times.
16.
Oh, I was doing 32.
Yeah.
What the heck? Oh my goodness. Thank you, and thank you for putting up with me. Good grief.
So your molar mass should be 0.02419.
Well, 11.8. So I had a student in class yesterday, and she kept saying, "Oh, I'm stupid." And I kept telling her, "No, you did something stupid, right? You're not stupid. There's a very important distinction, right? So look, I just did something stupid, and I looked at it, and I looked at it, and I couldn't figure out. Does it mean I'm stupid? No, I'm not stupid, but I do stupid things. So we're all part of the same club. Good grief.